Number 1, I see an equation that represents circle A, k is a constant, and they give us a point that lies on circle B. This B equation is going to have the same center, but twice the diameter. So I'm thinking if we complete the square and we get our standard form of circle A, we can then get the center and the diameter of circle B. Then we can plug our x and y in, and we should be able to solve for k. So let's start with completing the square. Remember, we just want to organize our x's and y's together. So how completing the square works is there's going to be a special number here that gets us kind of like a perfect square. So how we get that number is you take your b over 2 and you square it. So 4 over 2 is 2, squared is 4. So I add 4 here. And then for our y, we have plus y squared minus 10y. Same thing, take your b, negative 10 over 2, and then you square it. So negative 5 squared is going to be positive 25. And then you want to get everything else to the other side. So I would have already added 12k to my other side. So then it would equal 12k. And then don't forget, I can't just add 4 and 25 randomly. I would have to add 29 to my other side as well. Now we have our perfect squares done. We just factor this and factor this. So that's just going to be x plus 2 squared plus y minus 5 squared is equal to 12k plus 29. And this is going to be the standard form of our circle A. Don't forget that this right side is going to be our r squared. So if we want to solve for diameter so I can double it, well, I would take the square root. That would now represent r. And then I would multiply by 2. And that now represents my diameter. So if I want double that diameter, it just turns into 4 square root of 12k plus 29. But then if I want to turn it back into a radius squared for our new circle, so remember, this is the diameter of our new circle. To get the radius of the new circle, I divide by 2, so that becomes 2. But then to get the radius squared, I would square this, and we actually get back to 4 times 12k plus 29. That is going to be equal to the same center, so I can just keep my left side. And all I have to do at this point is Desmos. I pull up Desmos, I plug in my left side, so x plus 2 to the second plus, plus y minus 5 to the second. And this is going to be equal to 4 times 12k plus 29. And let's go ahead and expand this a little bit. There we go. And then all we have to do is we have to plug in our 2 points, or our 2 x and y values. So remember that your x is 8 and your y is 13. And then I just replace k with x, and it should solve everything for me. I see that my value for k is just going to be 1 here. Number 2, in triangle PQR, the measure of q is 90. So we can draw this off to the side here. We have P, Q, and R, and we have a 90. Next, they tell us that QS is an altitude. So we have angle Q already, and we can just make up that S is like over here. And an altitude is always going to form a 90 with the side that it's intersecting. They also tell us that PQ is 12, and the length of PR is 13 greater than PQ, so that's this whole hypotenuse. This whole hypotenuse is just going to be 25. And they want to know the value of QR over QS, which does involve our altitude, right? So what's nice is there are multiple ways to solve this, but there's going to be a big shortcut, and that is an altitude roll. So before we jump into the altitude roll, obviously we want to solve for this third side here, and we can just use Pythagorean's theorem. So if I do a squared plus b squared equals c squared, you just end up doing c squared minus the 12 squared, and then you take the square root. So we can just shortcut to this should be 25 squared minus 12 squared. And it is not the nicest decimal, so I'm going to leave it like that. But our altitude roll now is going to be your QS, your altitude, is going to be equal to your 2 legs multiplied. So PQ times QR, and then divided by the hypotenuse, which is just going to be 25. So what's nice is we can do a little bit of shortcuts here, right? So if they want QR over QS, let's do a little bit of math. We could cross multiply here, and we could get 25 QS is equal to PQ times QR. So our goal is QR is already on top. If we can get QS on the bottom, well, it's going to save us like a little bit of math in the future. So if I divide both sides by QS here, QS gets rid of that, And now I have QR over QS. I just have one final step. I want to divide both sides by PQ as well. PQ, that crosses off. And now I finally have it. QR over QS, which is what we want, is equal to 25 over PQ. So our final step, 25 over PQ, was 12. And it looks like our final answer here is going to be A. Number 3, I see a table with a constant in it that represents a linear relationship. And then down below, which equation also represents this relationship, and they are also linear. So I'm turning my brain off for this one. I'm just going to jump straight to Desmos. I'm going to insert a table. And I'm going to plug in 2 points from my table, 2k minus 7, also -2 with 13k minus 7. Little division trick, you just throw one parenthesis here, and then you can click divide, and then 3. And you notice this, this error for my two k values, and that's because k is not defined. So all I have to do is k is equal to 1. Those go away. I can go ahead and plot my graph now, and I see my line here. Now all I have to do is go down and then type my answer choices until one of my lines match. It really is that easy. So starting with A, k plus 2. Don't forget the little division trick. And then x plus 5k minus 1. And it looks like my line disappeared. I just clicked this on and off to make sure it does overlap our line. It's really that easy. I'm going to jump back, and we are going to answer A here. Number 4. A researcher compares two models that predict the percent of forage coverage in a region from this year to this year. Our first model looks linear, where P is the predicted percentage of forest coverage X years after 2000. M and K are positive constants. The second model can be written in an exponential form, where Q, similar to P, is the predicted percentage of forest coverage X years after 2000. N and R are positive constants, and N is greater than 1. Both models predict the same percentage of forest coverage, that's our P and our Q, our Y values, in the year 2008 and 2020. Well, remember, it's X years after 2000. So that would mean X is equal to 8 here, and X is equal to 20 here. So they want to know kind of how our graphs behave either before, in between, or after these two time periods, right? So I'm a very visual person. I would love to see these two graphs on Desmos with some random constants in there, with the restrictions that N is greater than 1, and that our Y values are equal when X is 8 and when X is 20. And it's going to be much easier to visualize on Desmos. So I pull my graph up here. And for our first equation, we say negative mx plus k. We throw some sliders in. And again, all they said is these have to be positive, so that's easy. Let's zoom out and see our linear line here. Our second equation is going to be negative n to the x plus r. And our only restriction here was that n and r are positive. Specifically, the n has to be greater than 1. So I'll just make it 1.1. The final touch is going to be these should have equal y values when my x is 8 and when my x is 20. So I want to drag these way up because I want to be dealing with positive numbers. So k is going to be our y-intercept here. Let's go ahead and make that like 40. And then same thing, my r value is going to be my, is our y-intercept? It's going to help us drag the y up. So we can bring that way up. And then I'll just leave the curved equation where it is, and we'll mess with our linear equation until I can try to get my y values. They don't have to be exact. I just want them to be close to help us demonstrate the relationship, right? So if I try to bring this up to maybe like 50, and then we can try to make the slope where it looks like it's going to kind of line up. Do you see how that looks like it might line up now? I drag this down. And honestly, I think that's close enough to see our relationship. Again, these aren't exactly lining up on our x equals 20, but you can kind of picture it if I moved it over a little bit. It looks like our curved line is going to be less than the linear line before this time period and after this time period. But in the middle of it, it looks like our curved line is going to be greater. So that's all I have to look for back on my worksheet here. I look down below and I see between this is our early period. Our linear equation is not going to be less. Our linear equation is actually going to be more in the earlier period. In the entire period, we're not going to have a definitive relationship because during some points, one's greater, during other points, another one's greater, so it can't be that. In C, this is our middle period, and it should say that our linear is less. The linear equation is less than the curved one during that period, 100%, but just to make sure. In D, after our time period, the linear equation is less. That's not true. The linear was more. So it looks like it's going to be C here. Number 5, the exponential function g is defined by g of x is equal to that, where c and d are positive constants. If g of k is equal to m, and the value of g of k plus 1 is 18% less than the value of m, where k and m are also constants, what is the value of d? So we're going to go through the kind of longer but more recognizable way first, and then we'll show the shortcut at the end. So what I would do is remember that when we have something in parentheses, they're saying that's our x. So we can say, okay, well, g of k is just going to be c times d raised to the k. And they're saying this is going to be equal to m, correct? And then the value of g of k plus 1 is 18% less than the value of m. It's the same thing. We're just substituting in for our x, k plus 1. And then this is going to be equal to 18% less than m. Remember, if I subtract 18%, I'll have 82% left. So we can do a little bit of algebra rules here. When it's d to the k plus 1, all they're saying is that's d raised to the k times d raised to the 1, because when I multiply bases, I add exponents. And this is going to be equal to 0.82m. And then I have two equations with m, and they want us to solve for d. So if I can get both of my equations to equal m, then I can substitute the other one in. So if I divide both sides by 0.82, divide by 0.82, that crosses off, and now this is equal to m, this is equal to m, and you see that we have a lot of like terms, so we'll probably be able to cancel stuff out. So I write my top equation to the k, that's going to be equal to c times d to the k times d to the first over 0.82. And our goal was realized because now we can cross off the c's on both sides, the dk's on both sides. There's that 1 there. And since we want to solve for d, I just multiply both sides by 0.82 by 0.82. That crosses off, and we get d is equal to 0.82, which is going to be answer choice D here. Now for that little shortcut that I mentioned, it can be a little bit jarring. That's why I like knowing how to do it this way just in case. But to go over it real quick, this is going to be an exponential rule. Anytime that you have an exponential function and you're plugging in like a g of k plus 1, k plus 2, all they're actually doing, remember the rule that we used right here where it was k plus 1, it was d to the k and then just an additional d to the 1. Well, that's what k plus 1 does. All it's doing is each plus 1 is adding an additional, or I guess multiplying an additional d. So k plus 2 would be d to the k times d to the first times d to the first, right? So our little shortcut here is g of k is equal to m. So g of k plus 1 is going to be equal to m times d, because there's that extra d. They're also saying that g of k plus 1 is equal to 18% less than m, which is 0.82 m. Cross off your m's, and you get d is equal to 0.82. So if that's jarring, it's fine. We have our other method. Either way, we get d here. Number 6, I see a system of equations, and they mention b and c are constants. Here's our c, here's our b. They say the system has infinitely many solutions, which we already know what type of problem this is. If I can get them both in slope-intercept form, I can set my coefficients equal, and with those equations, we can solve for b and c here. Also, to make it a little bit more familiar, I'm going to go ahead and replace my p with x, and then we will replace the q with y. And now it's going to be a little bit easier to get it in slope-intercept form. So up above, I'm going to add my 5y to the other side, and I'm going to kind of write it in reversed. So we have 5y. And then I'm going to go ahead and subtract the 9x from the other one. So that's going to leave us with 6x on the other side. And then finally, since this is the side y is on, c is going to stay positive. And then we do have to subtract the 41 over. So this is going to be my first linear equation here. And for our second one, we already have 11y over here. So I'm going to go ahead and subtract the by over. So now we have 11y minus by. And that's going to be equal to the hundreds on the correct side minus the 24. That's going to be 76. Let's write that at the end. And then we do have positive 24x, so we have to subtract it to the other side. So that's going to be negative 24x. So we don't have to finish slope-intercept form. Remember, we just wanted them to look analogous. And while it would be really hard to get my y-intercepts or the coefficient in front of y the same, look at our slopes. This is just missing a multiple of negative 4. So if I multiply this whole thing by negative 4, it's going to make a lot more sense in a second here. This becomes negative 20y is equal to negative 24x, and then minus 4c, and then plus 164. So your whole goal is to get one of your terms to match, whether it's your coefficient in front of y, your slope, or your y-intercept, because now these are the same. We can cancel those out. I can say that my coefficients here, if you want to be technical, what I would do is I'm factoring the y out. So it's technically a coefficient of 11 minus b in front of our y. So our 11 minus b should be equal to negative 20 because they're both my y coefficient. So add b to the other side, add 20 to the other side, and you should get b is equal to 31 here. And then for our second one, a little bit more confusing, we get our y-intercepts equal to each other. So 76 is equal to negative 4c plus 164. I would add my 4c to the other side. I would subtract 76 from 164. You get 88. And then finally, divide that by 4, and you should get off to the side here, c is equal to 22. Finally, b plus c, 31 plus 22, and you should get a final answer of 53. Number 7. The given function g models the value of an investment t years after it's made. Easiest way to think about this is when t is equal to 1, our 52,000 is going to increase by 6%. Which of the following functions best models the value of the investment m months after it's made? So again, when t is 1, our m should be equal to 12, and both of these should increase our 52,000 by 6%. So looking down below, when I plug in 12 for this m, I get 12 divided by 12, which is 1. This increases by 6%, so this is right so far. In b, I get 12 times 12, which is 1.06 raised to the 144. We want it to be raised to the 1 to match this equation up above. In c, when I do 12 divided by 12, I get 1, but it's times 1.0612, which is a little bit different than 6%. And finally in d, when I plug in 12, I get 1 for my exponent, also increasing by 6%. So this is a rare one. We're going to just have to test maybe another easy number, like when t is equal to 2. We're going to get 1.06 squared, which should be when m is equal to 24. So in a, when I plug in 24, this actually becomes 1/2, whereas when I plug in 24 over here, we do get raised to the 2, like our original function is. So it looks like finally D is going to be our right answer. Number 8, I see a table with 2 letters in it. They tell us there's a linear relationship and that this line also passes through the point 328. And they want to know what Q plus S is. So I'm thinking, jump on Desmos. We can get our line from these 2 known points, and we can use that line to solve for Q and then to solve for S. So I jump on Desmos, and we're going to add a table. We're going to plug in our first known point, which was -10, 2, and our second known point, which was 328. We go ahead and we graph it, and I can see my line right here. Now, what I can do is I can use my how to solve for slope, which is just your change in y divided by your change in x, and we can set that equal to +2. So for my first solving for slope, I'm going to take my second and first point. If you need to go back and take a picture of the problem, that's fine, or pull up the worksheet in a separate tab. My second point is going to be 18 for my y, -2 for my second y, and then I'm going to divide that by q minus the -10. So this is just my change in y over change in x. This should be equal to 2 because it should equal my slope, right? What's nice here is I just have to replace q with x, and Desmos will solve it for us. I go ahead and I zoom out to try to find my vertical line, and I see it right here. And just remember, if Desmos isn't giving you a point here, because obviously we can see it's -2, but there's cases where it's like a decimal, you do want to know how to get a point here. You just want to get first your equation equal to 0. So I would subtract 2 from both sides, and then you get rid of your equal 0. And while the equation changes, you still get the same point, except you can highlight it now. So on my paper, I'm going to highlight that q is -2. And then we can do our second slope equation. That's going to be my third point minus my second point. So that's going to be s minus 18. And that's going to be divided by 5 minus q. But we solved for q. I can replace this with -2. And I don't even have to change this part, right? We already took care of that. I'm going to replace s with x to solve for it. And I just got to scroll over to where I see my x-intercept now. And my s looks like it's going to be 32. I'll write that down, and we'll jump back to our paper. Finally, -2 plus 32. We're just going to get C here. Number 9. As a hot air balloon in the shape of a sphere ascends, the size of the balloon changes due to temperature and air pressure. A certain balloon's volume has an average rate of 5,000 cubic feet per hour. Which of the following is closest to the average rate of the change in cubic meters per minute? So it starts off sounding like we're in a physics class, but it does turn into just a basic unit conversion problem. With these, you always start with your initial rate. So we'll do 5,000 feet cubed divided by 1 hour. And all we have to do is we're kind of treating this like one big fraction. And diagonally, we want identical units so they cancel out. And then vertically, we want numbers that are the same. And we'll kind of go through an example here. So diagonally, I do 1 hour, because since this is a fraction, hours will divide by hours and it'll cancel out. And then vertically, what's equivalent to 1 hour that we want, and that's going to be 60 minutes. So already, just with one step, I've turned this from per hour to per minutes. And of course, to calculate my new rate, I would do 5,000 divided by 60, because this is just one big fraction. But now, the kind of harder part, we got to do the feet into meters. So again, diagonally, our units, we want feet, but specifically we want 3.28 feet because that's going to get us 1 meter. So I would put 3.28 feet diagonally because they'll cancel out. And then I put 1 meter up above. The problem is with this, we have feet cubed. So feet cubed is feet times feet times feet. So to cancel out with that, we copy them. So I have to do another one. 3.28 feet is going to be another 1 meter. And then finally, another 3.28 feet is going to be another 1 meter. Now let's make sure all our units match up. In the numerator, I have feet times feet times feet. In the denominator, I have feet times feet times feet. That cancels out. Now in my numerator, I have meters times meters times meters. So when I calculate this, I'm going to get meters cubed per minute. So we just want to do, the numerator is easy. That's just going to be 5,000. And then I'm going to divide by 60. And I'm going to divide by 3.28 3 times. And our final answer I'm looking at here is 2.36, or C. Number 10. A storage container is in the shape of a right circular cone. The container has a volume of 8640 pi. So we can pause right there. The volume of a cone is on our equation sheet. And if they ever give us like a value for that, we always want to set it equal. So we can say that 8640 pi is equal to the volume of the cone equation, again, on our equation sheet, which is 1/3 pi r squared times h, our height, and our radius. Next, they tell us the area of its circular base. So I think, maybe having a little bit of a picture. So here's our circular base. And here would be like the cone aspect. And then the height of the cone is going to be from the center of our circular base up to the top. And they tell us the area of the circular base down here is going to be 324 pi. Also on your equation sheet, don't forget, we have the area of a circle, and that's going to be the pi r squared part. So what they're actually saying is if this part is 324 pi, well then we could divide both sides by that, and we could solve for the 1/3 height, or especially just the height, right? So if I divide 8640 divided by 324, because the pi's are just going to cancel out, we get not the nicest number. We're going to get like 26 2/3 is equal to 1/3 height. So then I would multiply this number by 3. And we are going to get a nice number now. I'm going to get 80 is equal to my height. So we can start to label stuff now. We know that our height here is going to be 80. We can actually use this to solve for our radius too. We can say pi r squared is equal to 324 pi. cancel out your pi's, and then I can take the square root of 324, and I get 18. So we just solved for our radius as well. That's going to be down here. That radius is 18. And then finally, reading the rest of the question, they say, what is the slant height? So don't get your slant height confused with your actual height of your cone. Your height of the cone is if you're looking at it from like the front. Your slant height is this right here, which is just the hypotenuse of our triangle that involves our true height and our radius. So all I have to do is 80 squared plus 18 squared, and then I can do the square root of that. That's just Pythagorean's theorem. So 18 squared, that got us the 324. And then the 80 squared, that gets us 6,400. So that plus 324. And then if I take the square root of that, we should get 82 for our slant height. Number 11, I see a function with an absolute value in it. So you know I'm automatically jumping to Desmos. On Desmos, I'm going to type my function in, m divided by 4 plus our absolute value bars in the keyboard at the bottom, 2x minus 7, finish my absolute value bars, equal to 5m minus 6. So two things I like to change in my functions on Desmos. Number one, if it ever doesn't ask you for a slider and you have a letter in there, you just make your own down below. You just say m is equal to 1. That fixes my graph. But two problems here. I don't see anything. And even if I did see something, like it's because I don't have this slid to the right value. Notice how it's these vertical lines that don't really tell us much. And I also can't click on what their solutions are, right? It's a really good habit to get everything to one side of your equal sign. So if I subtract 5m over, so subtract 5m, that would get rid of this 5m. And then if I add 6 over, that would get rid of this 6 on this side, and it would be equal to 0. And then now you get rid of your equal 0. You can see my graph is technically the same. My two solutions are actually the same. It's just I can see them now. And now I can focus more on the question they asked. They said, what's going to give us exactly one real solution? So it's much easier to visualize on this graph because it's almost like a parabola. Like as I go this way, I'm stuck with two solutions. If I go too far this way, I have no solutions. So what I want is I want my vertex to be right on there. What's nice is they did give us answer choices, so we don't have to get down into the decimals here. I can just say, okay, does -6 over 5 work? It doesn't. Does 0 work for B? Nope. And finally, C, 24 divided by 19. It is exactly on there. It's really easy using Desmos this way. It's going to be C here. And finally, number 12, a scientist selected 67 island iguanas from one region and 76 sand lizards from another region at random in Ecuador. A pasture of defined scale inside each region was partitioned into uniformly sized artificial cells, and the specimens were permitted to roam in the pasture for a set amount of time. To monitor their activity, the scientists recorded the number of times the island iguanas and sand lizards passed through the artificial cells in their pasture during early youth and again during late youth. The scientists discovered that in early youth, the number of artificial cells the sand lizards passed through was notably more than the number of artificial cells the island iguanas passed through. They also observed that the number of artificial cells passed through by both the sand lizards and the island iguanas decreased from early youth to late youth. Okay, so there's really two main things that's happening here. Overall, we have two species from two different regions inside, one country. And in early youth, one of the species moved around much more than the other one. That's like our one comparison. That's a difference between the two. And then our second comparison is, it's actually kind of grouping them. It's saying both of them when they were earlier, or earlier in their youth, moved around more than when they were both later in their youth. So using these two comparisons and our general info, they want us to, which of the following statements is an appropriate conclusion that can be drawn from the study? In A, the statistically significant difference in activity during early youth between the two groups of specimens can be generalized to all island iguanas and sand lizards. Very much untrue. A super easy example would be if our study was on business people in New York, and they asked, could we generalize this to like all business people in the world? Well, even just from New York to Chicago, we might not be able to generalize business people because the cultures between New York and Chicago could be very different. You definitely could not generalize business people in New York to like different countries, like business people in Hong Kong, because the cultures are almost certainly different, right? So in this example, we can't generalize the iguanas and the sand lizards from Ecuador, maybe even to other regions in Ecuador, and especially to species that are outside of Ecuador. So A is going to be definitely wrong. In B, the statistically significant difference in activity during early youth between the two groups of specimens can only be generalized to the regions in the study. Now, this one would be really hard to argue against. So they studied sand lizards and island iguanas in two specific regions in Ecuador. So the results that I find from those two are very literally applicable to those two species in those two regions. B is practically just reiterating that the results of our study can reflect the things that we studied, right? So B, almost impossible to argue against. This is a really good answer here, but we'll still try the other two. In C, the statistically significant difference in activity between the two age groups was caused by aging. Now this one's tough. So A and B were more about the difference between the species when they were both younger. C is talking about our second observation, and that was when both of our species were younger, they moved around more than when they were both older. So right there, direct correlation is that they aged. It's possible that because of age, they move less, right? Huge problem with C, and this is where it turns almost more into like a reading problem, because there are a few on the blue books that are like statistically oriented like this. Did we control for climate? Did we control for changes to the terrain? Did we control for predation? Did we control for food resources, etc.? There could probably be 100 different factors that you could find in this creature's environment and in themselves that could change their movement over time. So C is your classic correlation is not necessarily causation unless I've controlled for all other factors. Is it possible that it's aging? Sure. Is it possible that it's one or a dozen other factors? Yes, because they didn't control for anything else in this experiment. So C is technically wrong. In D, the statistically significant difference in activity between the two age groups was caused by differences in region. Now this is kind of like a worse C. To reiterate C, at least there was correlation. They both aged and they both moved less. Possible correlation. Well, in D, both species moved less as they got older, but they're in different regions. So why would I be comparing two things happening similarly to two things having different regions? Like, if anything, D would be better if they ended up moving at slower speeds at different rates, because then it would be like, oh, the sand lizard being in maybe like a desert region, that could be why it's moving still more quickly at older age, whereas the island iguana in a different region is moving like at a slower rate at an older age. But again, our main problem with D is they're both slowing down, but they're both in different regions. So why would they share a similarity because of different regions? D is in the opposite direction. It's definitely not going to be that, and it's finally going to be B.